So we're here at Chavez, or 39th, at the start of this hill that slopes down into the Reed campus. And when my wife and I had this community garden a few years ago, we noticed that that hillside is really very stable. And in 20 years or so, it hasn't eroded. It looks like they've got some footings for that balcony there, probably pretty deep in. But my speculation is that that's cross-bedded gravel. And that's what the geologic map shows us. So we're going to be looking for places like that that have a steep slope, because if those were fine sediments, they would have eroded pretty quickly. And that's where you start to see landslides and so forth. What we're going to be looking for a lot today are trees that look like that. Because when you see a tree like that, it's called a pistol butt tree. It's got that bend in it. That means that over time the ground has shifted underneath it. And today we're going to use it as a proxy for where we're seeing fine sediments as opposed to the gravels. We're about to start down the hill. What fascinates me here is that there are many layers, at least 40, that created this topography. We started here before the last ice age 20,000 years ago with paleotopography. There was already a drainage from streams to the Willamette. We know that much. We don't know much about what it looked like. And then there were 40 floods that happened. And so each time the floods come out of the gorge, as they slow, they start to drop their heavier stuff. Some big boulders and smaller boulders and gravels. That thins off gradually, and then we get a second phenomena, and that is where the water pools, the silt and sand settles, and those overlap. So we get that all the way to the river. We got 40 of those floods. Each time there's an interval of maybe 50 to 100 years between the flood, and there's some erosion between them. Then there's another flood that covers it up, and another and another. That happens 40 times. Then we've got 13,000 years of erosion since. So all of that is layered into the hill that we're walking down. But if you look at the geologic map, it just shows you got gravels up there to the east, and you got fines to the west. So that's the simplification we're working with as we think about what's probably the complexity that's really actually under there. So we're heading down Ellis Street, and I guess the students are going to be coming down this way, or they're going to be starting here or a little further down. It's a private drive, but everyone walks through here anyway. A few years ago, my wife, who is an environmental scientist, put us on a campaign to get rid of the ivy here on this hill. Now, I objected to this because mostly I didn't want to do the work, but the other thing is I was worried that if we did take the ivy off, there would be a runnel, and the water would start coursing down and we'd get a big, landslide or slide. That hasn't happened, because it turns out that this hillside is just full of rocks. The good news here is, I think, that means that these are part of those cross-bedded gravels. And that's my hope. But I've been here for 30 years. This hillside has been pretty stable. And again, if it were fine sediments, it would have slid a long time ago. So these houses are now owned by Reed College here on 37th. They were constructed in about 1986. And that's about the time, according to the records that we've been able to see, that the wind dust point, the Native American projectile point, which is 8,000 to 10,000 years old, was found somewhere in this vicinity. Now, of course, that State Historical Preservation Office keeps a very tight lid on the location of those artifacts, and that's partially to protect the Native American heritage here. So we don't know exactly where, but we do know that it was found at a flaking site. That means that they were working the stone here. That's interesting for two reasons. One is, where were they doing it, and how much erosion has occurred since wherever they were exposed the flaking site. The other is, what was the material that they were working? There's not a lot, to my understanding, that's really good to make a projectile point in the Missoula flood sediments. There's basalt, there's quartzites, and I guess you could make an implement with a quartzite. But the better stuff comes from someplace like Mount Bachelor. It might have been traded at an obsidian or something. So, that's the question, is what was it made of, and kind of what was the site? Now, all of that is within really we're in what are called the ceded lands of the Grand Ronde tribe. And so it's really their concern. But I think it's important for Reed just to understand, as I did really for the first time, that these people were here. We've just entered the Reed Orchard here, and as you can see, it's starting to get really flat. We came off that hill, and here it flattens out, and the canyon is not far beyond. The interpretation here, based on the map, is that we're in the fine sediments. Now, whether we've got rhythmites underneath us or just reworked fine sediments over the past 13,000 years, I don't think we know. If we took a core, we might find that we're on top of rhythmites or just loose sand and silt. Probably a mixture of both. It may be no coincidence that as we move from the gravels and a little farther into the fines, we have springs north-south here at about 100 feet in elevation. Springs to the south, the Frog Pond to the north, all of them are right at about 100 feet. So they're sort of at the join of where the gravels and the fines meet. But the more likely explanation, I think, is just that there's a water table that intersects the slope at a certain level. Water tables follow the slope of a hill. But at a certain point, the erosion got to the point where the water table was exposed. And that's where the springs are, again at about 100 feet in elevation, all along this north-south line. We're heading down to almost 100 feet, and we're starting to see marsh here, where the water is coming up. It appears the water level in the canyon is dropping for 2 years straight. First the Frog Pond dried up last year, and then this year, this pond, which was dug out a few years ago out of marsh, this year has drained almost to mud. Although today, there's a little more water in it right after the storm we just had. But what this suggests, and I don't know if it's climate change or what, but the water level's usually pretty consistent in the canyon because the water table comes from all that apron of gravels that extends all the way to Troutdale. So that's just like a big sponge, and the water drains out here. It's usually pretty consistent over the seasons. It doesn't have a lot of seasonal variation, is my understanding. Check me on that. But there's some interesting questions here. One is, were the springs in other places when the water level was higher? And I think there's a place up in the Ramona Canyon, over yonder to the south, where the springs might have been at some point. And then as the water table drops, the water table intersects the slope at a different place, and we get the springs right here where they are currently. It may be that if the water level continues to drop, we'll see the canyon, the shape of the canyon changing. We'll see the springs coming out farther to the west. So this is one of my favorite spots in the winter because before all the grass and everything grows up again, you can see all the cobbles in the spring. And I mean, you can look right there in the sunlight. There's a quartzite, a nice orangish quartzite that's catching the light. What I'm curious about is, are there ways to characterize the Missoula flood deposits, the different Missoula flood deposits? Because there's about 5,000 years of history in those deposits from about 18,000 to about 13,000, and I get kind of fuzzy with the dates, so don't quote me. But the first floods probably brought whatever was in Lake Missoula, you know, all the stuff that had come down from Canada, including the belt rocks, just, you know, in the first torrents, a lot of that material was from Montana and Canadian origin. But as the floods proceeded, it's speculated, as the floods proceeded, there would have been less and less of that material and more of the stuff that got scraped out in eastern Washington. And those are mostly those Columbia River basalts. So we should see a trending toward more basalts. Now, I've only seen one study on this, but maybe your students can dig and find some more recent work on it. But it would be lovely to know, for example, when we see those cobbles, kind of where we are in the chronology. The other thing that is you want to point out here is these cobbles have been rounded by river action, by river and stream action. Not here, because the spring is just right around the corner. The spring is right behind me. So obviously these cobbles were rounded in a spring, these cobbles were rounded in a river or a stream somewhere else and then transported here. So they've had an interesting journey, both from being eroded out wherever they were in the first place, and then I just thought of something. The Columbia basalts that were scraped out can't be as rounded as the stuff that.
Well, question is, how far out were they rounded? So there was petrified watermelons out in eastern Washington, and those didn't travel very far, but they must have experienced a lot of erosion in the turbulence that they went through.
In a short period of time.
And so we could be seeing basalts here that are from 90 miles away.
It could be, and they've gotten. I mean, there must be a difference, though. But I just never thought of that.
Well, one could definitely do a geochemical analysis of the basalts and link them to a basalt flow. No question.
Yeah, it looks. Can you do that here?
Yeah.
So here we are in the main stem of the canyon, I guess, where it flattens out, and this is where the geese and the mallards love to hang out. I think one reason it's flatter here is because it's been dammed down by the salmon ladder, the fish ladder, and so it fills up with sediment. But now that we know there have been people here for 10,000 years, it's reasonable to wonder, like, how long has this been a lake, and how long has it been, of cultural importance, of economic importance? And one way we might approach that question is a kind of sensitive operation, but it would be very revealing, and that is to get a core from the sediment. And in that core, we would see alternating layers of biological activity that correspond to the seasons. And those are called varves. And with those varves, we might be able to date the length of time that the canyon sediments have been here. And I'd be very curious about that, because, I don't know, maybe this has only been here for the 100 years that the dam has been here, but I suspect that there are more sediments underneath, and those could go back hundreds or thousands of years. One of the real earthquake concerns is liquefaction. When you have fine sediments that have water in them, in an earthquake they just turn into liquid. And buildings on that liquefied soil collapse, and pipes come up, and really weird stuff like, sewer lines come up above the ground and so on. That would be a concern for campus because fine sediments there. But the water table here is about 40 feet under the level of the main campus. So I've talked to a couple geoengineers, and I'm no expert, and never allow an amateur's opinion to substitute for that of an expert in actual study of this. I'm sure Reed has done a lot of that. But the liquefaction chances are low if the water table is below those fine sediments. So that's our hope for campus. But yeah, you can see up there, it looks like there's some erosion, and that's more what you expect from hillsides like this. When there's sediment, they erode. It's the gravels that hold up much better. And I've got some great pictures that I'll drop in of those trees right next to the pond that are straight as arrows, and they are at least 70 years old. That's good news in my opinion, because it suggests that hillside has been really stable. We're standing on this land bridge with the fish ladder behind us, looking north. I'm not sure how long this bridge has been here, at least since Reed was built, so in 1912 or so. And it marks a boundary between where the silt is backed up and it's really flat, and then where it carves down more. And I think there's some rule or law or principle that when you put in a dam, it has the effect of carving out more of the stream below. But check me on that. In any event, we have this difference between the silted up area, which is relatively modern, and then the part of the canyon that we're going to move into, which is probably closer to what the original canyon looked like. It's steeper, and the stream kind of twists and turns. I want to stop here at this little diversion of the stream which comes through a pipe and point out something that's important when one is looking for native rocks These are rocks that have been brought in. These are probably Columbia River basalts or boring basalts. But I mean, this is pretty obvious in this case. But one thing you want to look for is stuff where there is there's construction, or maybe there have been rocks that have been brought in as riprap to hold back a bank, and kind of make the distinction between those rocks and the ones that were here already in the sediment. Now, of course, when people bring in riprap or they bring in construction materials, usually they don't want to transport them from very far, unless it's like building stone or something. So the likelihood when you see rocks like this, big chunky boulders, and you'll see them in people's yards at various parts of Portland, the likelihood is that they're still native rocks if they haven't been brought from too far. So that's a good guess here. If we were looking at, say, a wall in Commons or a wall at the old dorm block, that was transported by train across the country. But this, when you see just sort of riprap, these big boulders, those are usually from relatively close by. Sometimes you'll see in a riffle in a stream in between the bends where there's a straight part, you get the riffle where the rocks assemble. That's not the right word, assemble. They gather, the rocks gather. And then they're often kind of a situation like this where you have a lot of exposed rocks. So I'm not 99% sure that these cobbles are native, but I mean, they're not well sorted enough to come from a landscaping crew, probably. I don't know why they're gathered here. Whether this is the work of either hidden geologists or children or reedies. Let's just take a look. So right off there's a basalt. Looks kind of beaten up to me, but it also looks like it was vesicular. It has some bubbles in it and holes to begin with. So I don't know about that one. What else do we see? Pretty quickly, there's a quartzite. That one's not orange like your characteristic quartzite, but it might even be an agate.
Yeah.
It's very crystalline.
Wow.
We could expect to find anything in these Missoula sediments that came all the way from Canada. So we might find granites or gneisses, really metamorphosed rocks, but most of what I'm seeing here are basalts. There's another characteristic rock called Chalice volcanic, and it's a porphyry. It has big, typically pink crystals of feldspar that are maybe a couple millimeters long, and it's in a gray mass. And that comes from Idaho, I think. Here's a good spot to see native cobbles. They've been here for about 13,000 years. We're going to stay out of the stream again because of frog eggs and other environmentally sensitive things that live there. But we can, if the sun's right, you can get a good view of some of the different cobbles. I'm seeing orange. Orange could mean two things. It could mean basalts that have a high iron content, as they tend to, that have kind of rusted out, or they could be quartzites. Oh look, there are cobbles right at our feet. When you see cobbles in concrete like this, it's very likely that these came from a quarry in southeast Portland. And so even if you can't get down to the cobbles in the canyon, this is not a bad place to start to just look at the distribution. And heck, I guess one thing you could do is just count the number of apparent quartzites versus basalts and kind of come up with some sort of conclusion about the composition. So we're here at 28th Avenue, coming out of the canyon. And this is the place where the stream, having started up at the Ritmanis Pond and then coming westward, crosses 28th, and at the Rhododendron Gardens and Golf Course makes a left turn. And then it heads south until it intersects the Johnson Creek, and then it heads further south down to the Willamette River. And if you look across, you can see there's a lake over there. So we have a second set of springs. The first set was at about 100 feet in elevation, back up at the headwaters where the water table meets the slope of the hill and comes out at 100 feet. The second set of springs is at around 60 feet, roughly, here in the Rhododendron Gardens. Another set of north-south running springs that flow into the Rhododendron Gardens golf course and then down through Westmoreland Park and eventually to Johnson Creek and eventually to the Willamette. Now, one of the things that's interesting about that ancestral channel is that it starts all the way up at about Division Street in the Willamette, and then it arcs past Reed College all the way down to Milwaukee, where it intersects the Willamette again, where Johnson Creek goes in. So one theory is that that's an ancestral backflow channel for the Missoula floods, and that when the floods came in, they ponded in temporary Lake Allison and then slowly drained out to the sea, carving features as they went and leaving this channel. Another theory is that this was an ancestral Willamette channel. It's about the right width and has about the right ratio of 1 to 11 curve to width. Don't quote me on that. But that this might have been a spot where people were fishing for salmon that was coming up the canyon here at a vista that would have looked out into the Willamette. Maybe 10,000 years ago. Of course, that's speculation.